I'll make one comment about Peter's presentation because I can and it's my time. He credited me with using the word noodle, which may be completely true. He also said I was noodling over the weekend. That's less likely to have been true. Oh, here we go. That does work. So, the purpose of this presentation is to just bring you all up to speed a little bit with the limits that we have, some of the limits that we have in the interpreter. Not all of them. We'll talk about some limits and what we might do to alleviate some of those. Some of this content follows on from something that Richard Smith gave last year about an introduction to the workspace. And one of his slides last year said, some dramatic license has been taken and sequences have been shorted for simplicity, and I'm certainly doing the same thing here. Some of the issues we're going to talk about are, I'll just skip over a little bit, and certainly some of the proposed solutions and things we might do will be simplified in some cases. I also want to make the point that this is not an internal Dyalog APL developer meeting. I'm going to say things here that the interpreter developers might not agree with. They may have better ideas, but I'm trying to keep this simple. There's an implied hint here, which is don't come up at the end and ask me awkward questions. Also, coming up after this, Jeff Streeter is going to talk about some historical decisions that were made during the development of Dyalog APL, and he may or may not touch on some of the reasons for some of these limits. But these are limits, the sorts of things that we're talking about. Now, first of all, some of these things that are on this slide actually are only limited by the size of your workspace. For example, you can have an array of any arbitrary depth. Okay, it's only constrained by the size of your workspace. Something else that has always amused me as being only constrained by the size of your workspace is the length of a symbol, the length of a name in your workspace. You could create a variable, the name of which contains, for example, 39 million characters. That would suggest that the name of your variable is more important to you than the data it contains. And if you're doing that, I suggest you took a long, hard look at yourself. But what we're more interested... Oh, and another thing I did ask Jeff, why is Quad PW restricted to what we think these days is such a low number? Generally, people want Quad PW to be somewhere between 0 and... Well, not 0. Somewhere between 50 and 200, and then infinite. Okay, they're not particularly interested in anything in between. I asked Jeff why it was 32,000. He said, well, printers mainly. You don't need it any bigger because printers weren't that wide. So in some respects, you're lucky that it's that big already. But the interesting limits we've got are the ones that I'm going to talk about briefly today. Some of these will be quite obvious to you in terms of failing cases. If you try to create an expression that goes too high in rank, you'll get a limit error with a DMX message that says, well, we can't do that much rank. Limits that are to do with restrictions in the code that you write are a little bit more insidious in how they report themselves to you. Typically, you just get a digit back from QuadFX rather than the name of the function, which is what you get back if it had worked. I've been noodling with applying variant to QuadFX so that in the event of one of these limits being hit, you actually get a DMX message that tells you what has gone wrong. We'll talk a little bit more about this specific message as we go on. Obviously, the intent is that this will be irrelevant because we want to lift these limits to a point where you never see them. So let's talk about some of the generic problems we generally have in Dyalog APL that lead us to have these limits. And let's talk about rank in the first instance. Here is a slide from Richard Smith's presentation from last year where he talked about the layout of a pocket in Dyalog APL. And typically a pocket is our unit of allocation. And typically all of our pockets begin with this LRZ triplet, which is essentially what we call the length, the ref count, and the zones. And Asher yesterday, and each of these are 32-bit fields on a 32-bit interpreter and 64-bit fields on a 64-bit interpreter. Except in 64-bit interpreters, we don't use all of the bits that are in the zones. That turns out to be quite key. Asher had this information on one of his slides yesterday. Here we have a pocket that he extracted from the text representation of a WSDump. And there you see the length, you see the ref count and the zones. And then following that in memory is the payload. Oh, hold on. I spoke quicker than I was clicking. There's the payload. And he then showed this image where what we see in the green box at the bottom is essentially information that's encoded in that zones field. Okay, so let's dig into that a little bit more. In an array pocket, the zones are split up into a number of fields. A type, and that tells us that this pocket contains an array. There is a field that says what the rank is, a field that says what the L type is, and then there's a bunch of other stuff. But crucially, the field that contains the rank is only 4 bits wide. Therefore, we can only store the value 0 through 15. That's why you have the limit of max rank of 15. Also, we only have 4 bits to store the element type. So, you know, you've got 3 widths of integers, 3 widths of characters. We've got 2 types of floats. We've got complex numbers. We're getting close to hitting that limit of element types as well. You know, and also we can only have 16 pocket types. So what would be nice is if we could just widen all of these things to give ourselves the luxury of more space. So if we widen the rank field to 8 bits, have I got a bracket for that? Yeah, then we could go to rank 255. I'm not suggesting we do that, but it would be nice to give ourselves the flexibility to maybe go to 32 or 64, knowing that there's space there if we want to go to higher later. And we've also added more room for element types, and if we widen this field as well, not only does everything here become byte aligned, which means it probably perform quicker, but then we also have room for more pocket types. So, great, we'll just do that and it's easy. There are workspaces. There are a lot of workspaces out there that have got arrays in with the old format. So every time we load an old workspace, we'd have to convert that from the old format to the new format. And it's doable, but it takes time. There's old component files out there which will have arrays on. There may be old serialized data that's been saved in your proprietary system. We have IBMs and mechanisms to serialize an array to a sequence of bytes. You might have saved that to a file somewhere, and then you might give it back to the interpreter in the future. We might need to fix that up. More usefully for you, but something that adds a complication for us, is that we've always said that when you write an array to a component file from a interpreter, then it will be readable by all old versions of the interpreter. Okay, so if we change the max rank from 16 to 32, plus or minus 1, we want to be able to save, let me rephrase that. If we widen the pocket so that it is possible to create an array of higher rank, all of those fields are in different positions. Old interpreters won't be able to read them. Okay, so we feel obliged to, going forwards, if we change these layouts, provide a mechanism where by default, old interpreters will be able to read these arrays as long as they don't have the high rank. Okay, so we need to have the ability to save these pockets in the old format so that old interpreters can continue to read them. And that's an extra dimension of complexity that we have. Talk to Richard about this because he does all the component file stuff. My eyes glaze over very quickly when we start doing that. So that's one thing, one problem we've got. So the next problem I want to talk about is the one that generated the limit error with the variance on quad effects. And this is something that comes a little bit more to the fore when we start talking about array notation. And this is the limit of the number of constants and names that one can have in a function. Let's consider this line of code. X is a reference to a symbol, and this entire simple array is a reference to a single constant. That's the vocabulary I'm using here. These references are stored through what we call a local pocket, which has a length ref count zones, and then it has a payload. For this piece of text, the payload is 2 elements because there's a payload which is a reference to the thing X, and then the second element of the reference of the payload is a pointer to the 1, 2, 3 constant. Okay. If we have another 1, 2, 3 constant in the same function, then it's shared in the payload. We're only consuming 2 elements of this payload for the symbol and the references to the 2 constants. Which means that if we had a large amount of array notation, this would consume a slot in the pocket, this would consume a slot in the pocket, as would this. This fortunately, is just bumping a ref count essentially on the others. So not every row in a array notation matrix is going to cause us problems. But if we encourage you to write array notation, you're potentially going to get closer to this 4096 limit that we've got. And we've got this 4096 limit for the same reason that we have the 15 limit in 15-bit, sorry, the 15 limit in rank. We've got a field here which is 12 bits wide. So there's a maximum value of 4096. So we need to find a way of widening this so that we can get away from this potential problem. It's worth pointing out that this problem exists regardless of how you use these literals. Okay, array notation doesn't introduce this limit more, but it maybe exposes it to you more because we are encouraging you to write your arrays in that manner in code. So what we could do, okay, right, also, so this zones field is full. All of the bits in these 32 bits are consumed. Fortunately, as I said earlier, on 64-bit interpreters, there's 32 bits here that we're not using yet. So we can move these fields across and widen them into those free bits that we've got in 64-bit workspaces. So we could, in theory, without doing too much, have 24 bits of these things, which would give us a maximum value of, 16 million constants in a function, which is pretty good. For other reasons that we'll come to in a moment, we actually need to restrict that to potentially just 16 bits. Okay, which is still, 65,000 unique constants in a function. Or references to variables, it's all the same thing. A consequence of this is because we need to allocate those extra 32 bits, then your 32-bit workspaces, if you have them, may get larger, and we can have a conversation about that towards the end of the presentation. Going through the interpreter, there are a number of these fields that are constrained by their width in bits. This is just a bash expression that tells me there are 142 fields in the interpreter that they're not integers, they're not floats, they're just constrained by a number of bits in the structure. And in theory, we should look at all of those and say, are these limits that we can move that need to be extended? Another one of these limits appears in what we call a body pocket, okay, which defines essentially a function header, and it's got a line count field in it, which is also 12 bits wide, and this is why we have a limit of 4,096 lines in a function. Okay, same problem, we've got this field of fixed width, so we've got to figure out some way of widening that so that we can have a bigger number for the number of lines in a pocket. Fortunately, in this body pocket, there are some unused bits, and we may be able to manufacture a way of splitting the line count between the two parts, or better yet, restructure this in some other way so that we can just have bigger numbers. So it's easy, isn't it? We just do that, and it's fine. Now, because we've got old workspaces, we have to convert everything on the way in from. We've got component files that we have to convert everything on the way in from, and so on. Fortunately, we don't make the same promise, I think, with functions, that you'll be able to read them from old interpreters, so at least that problem is a little bit easier for us. It's the same joke, don't worry. So, let's look a little bit more at this constant symbols limit that I mentioned that was 4096. When we process a line of APL code, we convert it into a sequence of tokens. And this is now going to get a little bit technical, but I was struggling to try to get this information across to you without getting technical, so forgive me if we have to do that. So when we process a line of code, we convert it into a sequence of bytes that we then go through one at a time to figure out what's going on. So with this line of code here, we have a token 57 in the byte stream, which tells us that the following 2 bytes are an index into that local pocket. So these tokens tell us that it's the reference to the 1, 2, 3. And then the 57, followed by the 2 bytes that we see here, are our reference to X. Okay. So these are 16-bit fields, comprised of 2 bytes. So these slots allow us to go to 65,000. Okay, which is great, because at the moment we're only using 12. If we widen those local pockets from 12 to 16, that's in theory all we need to do, because all of this stuff just works. It's already got room for bits that we're not using. So, it's fairly straightforward to go from 4096 limits to constants in your function to 65,000, which means that 4096 all of a sudden becomes that. That's an improvement. currently with this layout, there's not room for any more. So that brings us to the next thing, which is basically the size of functions. Okay, now currently we've got a limit of 4096 lines in a function, I mentioned that. Morton said in one of his slides that we've got migrants coming from other APLs who have functions with more than, I want to say more than 10,000, but that's not what he said. What he said was more than 9,999, so that's why that says that. So that makes us vulnerable to these limits. And as I said, we had 4096 limit of line counts. But what's key about that is here is a sequence of code, and this is probably the simplest but useful line of code you could have in a line of an APL function. And this breaks down into these bytes. We've got the same thing. We've got a 57 that tells us there's a reference. We've got a byte that tells us we're going to do a catenate. We've got 3 bytes that tells us what the next reference is. We've got a byte for the assignment, a byte for the reference for the result. And then we've got this just token at the end that just says, well, that's the end of the line, you're done. So this is 12 tokens for a line that pretty much does the bare minimum. Okay. We've got a limit of 65,000 tokens in a function. Okay, we'll come back to why that limit exists in a moment. So if we go to 10,000 lines, that are basically just doing the bare minimum you can get away with, it's too big, we can't do that. So we need to address this 65,000, look why we've got that, to see what we can do to alleviate that problem. There's a vocabulary issue here, okay? I use the word problem. I don't mean problem, I mean we want to alleviate a limit. Even limit is a bit pessimistic. We need to meet this challenge, that's what we need to do. So, what do we do to change function too large? Well, before we do that, let's look to see what it is that makes a function too large. Here is a larger APL expression. Let's just distribute that amongst the tokens. Okay, we've seen these things before. That's your 1, 2, 3 and your X. Let's just go right to left just to fill in the dots. Hopefully we've got time. So the first token there is a 66, that's a diamond. Okay, there's no diamond at the end of the APL code, but because there are some in the body, there's an implied one at the end. After that, there are 2 bytes, which are a link to where the next diamond is. Okay, so there's a diamond with 2 bytes. There's a diamond with 2 bytes. Okay. Next token over here is a 6F, which tells us there's a control structure coming. Okay. Following that is the 5 that tells us what control structure element is coming. And then there's but it could be any of these things. I mean, it could be more than just these things, but this is an interesting set of control structures that might appear here. Well, that saved us a certain amount of time. The point here is that the control structure elements are followed by 2-byte offsets. And they're offsets into the payload of the pocket to the other end of the control structure element or something that's in the middle. So we can't make our functions bigger because this token stream doesn't allow us to specify offsets between bits of code that need to know where the other end is. Okay, so what we need to do is we need to come up with a way of stretching this representation out so that these offsets become 4-byte offsets. Okay, we can do that. At the same time, and that's about 4 gigs, that gives you 4 gigs worth of function, which is if your functions are bigger than that, like the variables, take a long hard look at yourselves. While we're doing this, we might also want to extend the offset for diamonds. Okay, but having diamonds which are more than 65,000 tokens, I mean not text, but compiled tokens essentially, having those apart, maybe that's not necessary. Again, look at yourselves. But what might be a good idea is to extend the tokens here for the 57, which is where we've got the references to symbols and constants. Okay, if we widen that from 2 bytes to 4 bytes, that means we can have 4 trillion unique constants in our function, which means that 4096, which you've already said, let's improve that to 65,000, all of a sudden becomes whatever that is. It's 4 trillion approximately. At this point, I say, yes, array notation is a good thing, but if you have 4 trillion literal lines of array notation in your function, we're looking at ourselves a lot here. So it's easy, isn't it? All we've got to do is just that. Well, I mean, again, I've told you this story about why we haven't just done this yet. So those are the problems that I wanted to bring your attention. They basically fall into two categories. One is we've got these zones in structures, in pockets, typically in the headers, but they could be in the payload, where in order to lift those limits, we've got to make those things bigger. And in 32-bit interpreters, that might mean that we need to add more space into every pocket because we need more room in the zones. If we're going to widen all of those offsets, okay, you might have a function with a lot of control structure elements in it. And it's worth bearing in mind that defun open and closed braces are each a control structure element. New lines in defuns are control structure elements. Okay, so it's not just your colon ifs and your end ifs. There are a number of things which, for good reason, inside the interpreter are implemented as control structures because they are linked elements within your source code. I did some back-of-an-envelope calculations. I reckon that defuns.d was, if we extend all of those offsets, gets about 2% larger, so it's not significant. This single function, which is hex, let me get out of the way, I reckon would probably get about 3% larger. So it's not vast amounts, okay? But if we wanted to add 32 bits to the beginning of every pocket, then that might be a bigger overhead onto the sides of your saved workspaces. Okay, this is just an additional complication. We might want to, let me just skip through that. We've got our 6F keyword tokens, which consume 2 bytes. What we might need to do is to introduce new tokens, FF, to mean keywords with 4-byte offsets. That's something else we could do. The problem, the challenge that we need to meet there is that the tokens themselves are in this byte stream. So they become resources that we need to be careful of as well. I mean, we could have multi-byte tokens, but then we get into other complexities and other challenges that we need to meet. So there's a lot of considerations here. It all basically just boils down then to, we also might want to increase the number of control structure elements or increase the control structure depth, because currently that also has a limit because it's in here in a byte. So it's easy. Well, yes, but there's a trade-off. Workspace size versus interpreter complexity. And even that's not simple. You know, if we make the workspace bigger, processing the tokens might be quicker, so you might think the performance is better, but all it takes is one extra compaction when your application is running, and all of that time is lost because you spend all that time doing the workspace compaction again. So, and finally, the thing that makes it difficult, again, is always this element of backwards compatibility. So the point is that it is, on the face of it, a tantalizingly simple thing to do. We can change our structures, and everything that we do from that point onwards will just work. If we didn't have any saved workspaces, you could just write your APL code, and it would just work in all these new these new limits. But because we've got a load of workspaces, I mean, you might not be using them now, but there's a lot of old code out there in workspaces, and you need to be able to get it in and use it. So we need to be able to convert it on the way in. That's where the challenge comes in this stuff. And also making sure that any changes we make now, we don't wish that we did something else 20 years down the line. Okay? So we got 1 minute left, which is great because I think I can end with a more optimistic note, I suppose, which is, you know, we can do it. It's all doable, and we talked about a few of these things. We can do some of them without doing the others, but there's always this knock-on effect. Okay, so we can increase the number of tokens constants, but that doesn't really make sense if you can't write functions that are big enough. So let's increase the number of lines. If we increase the number of lines, that really only makes sense if we then increase the size that a function would be in terms of the number of bytes that it compiles into. So, you know, again, we've got that trade-off is what's the sweet spot to hit in terms of what we do now and what we do in the future. And I think that's it. So I think I've got 3 minutes for questions, so I'll take them now. I reserve the right to tell anyone who's awkward that that's awkward, and I'm not going to answer it. Thank you.